Okay. Okay, shall we begin? So today we have the first of the fun things, and by fun I mean not fun at all. I mean actual statistics, the stuff that may scare some of you, but it shouldn't, because it's pretty straightforward. And for some of you, again, it might be review. For most, I imagine it probably isn't. So we're talking about standard deviations, z-scores, percentiles, standard scores, and so forth. Really things that we don't use a whole lot anymore except in standardized testing. But it's kind of an important fundamental, an important basic to get your mind around before we can do anything else. So I'll try to go slowly, and again, this will be on YouTube, so you can revisit my words of wisdom at your leisure. So we begin with this. Last time we covered our, is that too bright? Let me see. Ooh, much better. Oh, and YouTube likes that better too. All right, that's good. So last time we covered measures of central tendency. We have mode, median, and mean. I think we all know what that is now. We did it to death. And we covered two measurements of variability. The important one was the interquartile range. That was the harder of the two. And just do some practice exercises and it'll be clear. Remember that we're trying to compute Q1 and Q3. Q2 is always the median, and the range is between Q1 and Q3. So we have two more measurements of variability we're going to go through, and they are the standard deviation and the variance. And they're essentially the same thing, because the variance is just the square of the standard deviation. So we can compute one of them, you can compute the other. And it's the most common measurement of variability. That's why they call it the standard, because it's the standard. So it is an index that tells us typically how much the scores, the values in our data set, differ from the mean. So we have that word deviation. I mentioned it earlier. A deviation is how much your individual score is different from the mean. So essentially it is the score in your data set minus the mean value is your deviation. In this case, these slides were provided by the textbook manufacturer, so I put up with that. I wouldn't use this terminology otherwise. So in this case, each individual deviation score is just the difference between individual score and the mean. And the standard deviation is going to be the standard, the typical deviation score. So in a given distribution, like I mentioned, almost everything in the world, especially every human characteristic, is distributed normally like this. So if this is, I don't know, the heights of a million people that I sampled, right? So this would be the frequency, and this is the actual height. So here, maybe 5'7" is the most common height, right? And over here, maybe 6 inches tall is the least common height for adults. And over here, we got giants who are 10 feet tall or something. So in every human characteristic, there's going to be some extreme individuals, but most of us will be right smack in the middle. And an amazing thing happens for a characteristic that is distributed normally. If it's a perfect normal distribution, as we hope many things are, nothing really is, but many things come close, then one standard deviation from the mean is exactly 34.1 cases in either direction. So in any given sample, 34.1 percent of people will be less than my mean value, and 34.1 will be more than my mean value. Now, two standard deviations from the mean, I've got around 95% or so. So add these two up, I get 47 times 2, 94, 95%. Right, will give me two standard deviations from the mean. And the more deviations I get from the mean, the more of my sample I get. Right? So that's why we like to think about things as the numbers of standard deviations away from the mean. That tells me how many people likely have this characteristics. So again, if I figure out that the average human height is 5'7", and my standard deviation of the population is, I don't know, 6 inches, then I know that 34.1% of people are probably going to be within 6 inches less than 5'7", and 34.1% will be 6 inches more than 5'7". That's kind of what we're talking about here. So here's an example. This is weight in pounds of a bunch of people. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people. The mean is going to be, add them all up, divided by 10, we get 150. Convenient. right? So my deviation scores is going to be each of these minus the mean. So at the low end, 110 minus 150 is minus 40. At the high end, 190 minus 150 is plus 40. Those are my deviation scores at the endpoints. But when I get closer, the deviation scores kind of get smaller. This is only 10, that's 20, and so forth. So a deviation is how much each data point deviates from the mean. Right? A standard deviation is going to be the typical deviation score. So we need to determine what typical means. So here's my data again. And for each of these data points, I computed the deviation. So 110 minus 150 is minus 140, and so forth, and so forth, and so forth, and so forth, and so forth. If I add up all my deviation scores, what do I get? Magically, I get 0. It's not magical at all. It's expected. Right? So that's always the case. The sum of all my deviations is going to be 0. So if I add them all up and divide by 10, I always get 0. So the average deviation score tells me nothing. It always ends up being 0. So instead, we like to square them. As I mentioned last time, one way to get rid of the negative signs is to square things. So we're going to square all the deviation scores, then divide by the total. Notice here I say I'm squaring and summing them all up and dividing by n minus 1. Not n, but n minus 1. There's a reason for that, and you don't need to know what that reason is. It has to do with just the nature of large numbers, and we actually call that n thing the degrees of freedom. It is a sample size, but degrees of freedom is the number of dimensions, shall we say, that something could exist in. So if I know n minus 1 characteristics, I know the nth one as well, so I don't need to divide by the total number of n. Don't worry about the details. Really, it's like a 2-hour conversation to go through why it's n minus 1 and not n. And frankly, I still probably couldn't convince you because I don't fully understand it myself. So one of my grad students actually tweeted me yesterday asking for a succinct definition of why it's n minus 1. I don't know. I sent him to a YouTube video instead. So here's our data here. So we take all of our data points, we subtract from the mean, we square them, we add them all up, and we divide by n minus 1, and we take the square root, and we get 25.82. I just applied that same formula to my data. So my standard deviation is 25.82 for this sample. Remember, the extreme deviation scores are minus 40 and plus 40, but the standard one is 25.82 because that's what most of the points seem to express. So, a little bit by notation. We use this squiggle here called the sigma for the standard deviation in the reference population. Remember, that's a parameter. If it's in the target population, we call it a parameter. And we use small s for the standard deviation in the sample. So this is a statistic, and that's a parameter. Okay. The textbook uses SD for both because the textbook is trying to be modern and cool. The textbook can be annoying at times, but recognize that mathematical sticklers prefer this. I will use all three just to annoy you. And also because oftentimes in making exams, I can't get a sigma on the typographic paper, so I'll use SD instead. Okay. As I mentioned, the standard deviation gives us a typical amount. In this case, it's an average amount of deviation from the mean. It tells you how wrong, on average, your data point is. So if the average height of everyone is 5'7" and your guy is 5'2", then you know he's deviated from the mean a certain amount. And how different is that from the standard deviation? How different is your guy, your data point, from what is expected to be different? If that makes any sense. Okay. Now, a standard deviation provides a particular kind of instantaneous bit of information about your sample. I showed that to you already by pointing out that one standard deviation is 34%, 2 standard deviations is about 16% away from that, and so forth. And that's standard. So we look back at this again. There's a fixed percentage of cases from the mean at all times. Right? So we like to actually think about usually this chunk in any given distribution. 2 standard deviations is where most of our statistics seems to apply. And that gives us about 95%, a little more than 95% of all cases. 99% of all cases will fall under 3 standard deviations. And the more deviations I go beyond the mean, the more cases I capture. But as you can see, because there's so much fewer cases beyond here, I'm getting less and less return for my money. I expand my detection parameters, but I get fewer and fewer cases. Whereas here, I get most of them. Here I get 95%, and so forth. Okay, so a person who scores 1 standard deviation below the mean has a higher score than 16% of the cases. How do we get that? Go back here again. So let's say let's say this is a distribution of MCAT scores. Got everyone's attention, so everyone thinks to go to medical school. Right? So, and this actually is relevant for standardized testing. So if this is a distribution of MCAT scores, and you score, and the typical mean is over here, and you score here. You score 1 standard deviation below the mean. You are better than this amount of people. You are better than 13.6 plus 2.3, so about 16% of the people you are better than. If you score 1 standard deviation above the mean, then you got about 84% better than everybody else. So 50% plus 34.1. Okay. And that takes us to the topic of percentiles. So when you write standardized testings like LSATs and MCATs and GRE, they compute percentiles, not percentages. Your percentage is what you scored on the test. Your percentile is how you scored relative to everybody else. Why is that more relevant than a percentage? If you're writing an MCAT, for example, why is your percentile score more relevant than your percentage, do you think? So I'll say it again. A percentile tells you how much better you did than everybody else. A percentage tells you how well you did on the test. Yes?
They don't want to know how far you got. They want to know if you're better than everyone else.
Yes, but also think about it from year to year. So you may get, this particular year, a bunch of dumbasses writing it, right? But we got to take somebody. So, right? So let's say everyone fails. All it matters is that you're better than most other people. Or maybe you get a bunch of geniuses when you're writing it, and everyone gets over 90, but we're only taking a certain number. So all we care about is the ones who did better than everybody else. So again, how you did on the test doesn't matter, it's how you did relative to your competition that matters. That's where percentiles come in. That way we can compare from year to year. Right? Yes?
Does this still apply when we have skewness in the...
No, not really, no. So this only applies if we have symmetrical distribution. So what we tend to do is we transform the data to resemble a symmetrical distribution. And we won't do transformations in this class, but there's an implied transformation in some of the equations I'm going to show you. When we compute what your percentile ranking is, we're actually transforming your personal curve to match the general curve. And we'll see what that looks like in a second. Okay, so a person who scores 1 standard deviation above the mean, right here, scores 50% plus 34.1, 84.1% better than everybody else. What you want to be is over here. We're scoring literally 99% more than everybody else. Okay, so the advantages of a standard deviation is that we're taking all the data into account. We're not just looking at the endpoints or the mean, we're looking at everybody and how they differ from the mean. It's a more stable than range or IQR. What does stable mean again? Yes?
Similar from sample to sample.
That's right. So how many samples I take, I'm probably going to get the same result. And we use standard deviation, you'll see in the future, to compute all kinds of other fun things. Right, so bad parts. We can have extreme scores that mess with it. So if we have a lot of outliers, my distribution gets kind of flattened out. It gets more platycritic, right? And that affects my numbers. And it's clearly not as intuitive because I'm struggling to explain it to you. If it was intuitive, it's, oh, that makes sense. Let's move on. But I've got like 6 slides to explain it, just to make sure it's drilled home. Intuition is good. Now, a variance is just the square of a standard deviation. It's important, and it really measures the amount of interplay, of variation in your sample. It's hard to understand intuitively. So in our previous example, the variance would have been this squared. In this case, the number of the beast. Number of the beast is wonderful. Right, so it's an evil number of variance. You can't trust the variance. Tough crowd, tough crowd. So we can't interpret it well because it's not in the original units. So if my sample here is pounds, right? My standard deviation is also in pounds. The typical person is 25.8 pounds away from the mean. The variance is pounds squared. Doesn't mean anything, right? That has no actual physical meaning. It just has a mathematical meaning. So keep that in mind. The variance is the unit squared as well. So more about notation. The sigma, we mentioned, is the parameter, the standard deviation of the parameter. Small s is the standard deviation statistic in the sample. Sigma squared is the variance parameter, and s squared is the variance in the sample, the statistic. Makes sense. Okay, here are my formula for variance. Okay, now I've screwed you up a bit, haven't I? Because I said it should be n minus 1 as denominator. But that's only true in our sample. So if we can compute the parameter version of either the standard deviation or the variance, we use n as my denominator. If I only have a sample, we use n minus 1. Okay, it's exactly the same thing, but we almost never have the population. We almost always have the sample. Sometimes we have this. We have a census, for example. Like I measure everyone's height, everyone's age, whatever. Then I can use n. Obviously, with a large enough sample, it doesn't really make that much of a difference. But that's the nuance here. That's important to know. Okay, here are, we showed this last time. These are how we use variability depending upon the nature of our data. The standard deviation and variance only apply when we have continuous data that's interval or ratio. If it's nominal or ordinal data, we can't use it. Now, that's true, but I'm going to give you a bit of a wink-wink here. And the wink-wink is that if we have large numbers of data that are ordinal, we sometimes pretend that it's interval. Okay, so that may come up later on, and I'll point it out when it does. So in real life, again, if I've got literally tens of thousands or hundreds of thousands or millions of data points, like in large health surveys that could be ordinal, I would pretend that it's continuous. I can use these variability measurements, which is technically not correct, but we do it anyway. Right. So relative standing is that aspect of using standard deviation that is relevant for computing your standardized scores, that everyone wants to know about when it comes time to write your MCAT and your LSATs. You'll go back to these slides and go, what does he mean by that? And what I got is important. Okay, so what we're looking for is your position, your relative standing in a distribution, your percentile rank, also a standard score. So a standard score is how many deviations from the mean your thing is, and a percentile rank is how many deciles, quartiles, whatever above it is. So a percentile is 1/100th of a distribution. So in my normal curve, if I divide that by 100 bits, 1 percentile is 1 of those hundredths, and so forth. A quartile we've done already. You've already done quartiles. So that's why we distribute we separate my distribution into fours and a deciles into tenths. Right, and so forth. There's quintiles and trientiles. Again, in this class, I only ask you to compute quartiles, but the percentile we'll use right now. Yes. Yes. So in exam questions, I will specify which significant digits to use and how many, so forth, or I will make it so easy that you only get one answer. I hope. I got in trouble in the past for that, for having complicated questions. Well, if you did it this way with this number of digits, you get different answers. So now I make it pretty clear. Yeah. Okay. Somebody asks me that every single year, and every year I forget to address it. So thank you. All right. So a percentile rank is a location of your score in the distribution, as I mentioned. Okay. So if you have a score, we'll see what a score looks like in a second. It allows you to compute your percentile mark. If you have a percentile, it allows you to compute your score. Right. So before I do examples of that, we have to talk about outliers as well. An outlier is something that it is an extreme value in your data set. Like I mentioned, if I'm doing the heights of people, most people are 5'7", you know, some people are a little shorter or taller. I want to get someone who's 6 inches tall. Like the shortest man in the world is like 7 inches tall or something. Seriously. And the tallest man in the world is like 12 feet or something like that. So those are outliers. They're not typical. And they're probably not more than 1 or 2 of them. So we need to control for outliers in our data. We have to define what outlier is. We have mild outliers and extreme outliers. A man who's 7 inches tall is an extreme outlier. Right? A man who's 4'10" is probably a mild outlier. And that counts for pretty much everything. I think I asked you before who the youngest mother on record was. Did I ask you that? Right. So that's an extreme outlier. That's not typical. So we need to compute that. So if you read the Gladwell book Outliers, don't. It's horrible. It's Gladwell I can't stand this guy. It's a fake epidemiologist. So don't talk. So an outlier is an observation that is markedly different from everybody else. Okay, so in this course, we follow the textbook definition of what an outlier is. So an outlier is a value that is 1.5 times greater than the interquartile range. That's why we compute the IQR. One of the reasons is so we can now identify outliers. So we say that a mild outlier is one with a score that is between 1.5 and 3 times the value of the IQR, and the extreme outlier is one that is more than 3 times the value of the IQR. Okay, so let's see how that looks. To visually depict outliers, we use what's called a box plot or a box and whiskers plot. Has anyone seen a box plot before? Oh, yeah, good. Okay, so it's really popular in population sciences, and it's amazing we don't introduce it earlier in high school. So a box plot instantaneously allows you to see the median, sometimes the mean, the IQR, the range, and the outliers. So here's an example of a box plot. So here's my data. This is the IQR of my data. And this is the median of my data. My mean, sometimes I could put it in here, right? And this is the range of my data. Now, people kind of differ on whether or not the range should include the outliers or shouldn't. And I conform to the textbook definition for this. So the textbook says that the box plot does not include the range. The box plot only includes those that are not outliers. So I'll say that again. So let's say we had a couple of points here that were outliers. We would not include that in the box plot. We would stop the box plot before that. Okay. So I'll show you what that looks like in a second. So the bottom of the box is Q1. The top of the box is Q3. There's a line in the middle, which is the median. The whiskers is the range that does not include outliers, and the outliers are shown as points. SPSS will compute these for you, and they'll show a mild outlier as a 0, and an asterisk is an extreme outlier, like this. So here's some data. So here we have, see, the range actually includes all of my data, but because SPSS does it and textbook likes it, the box plot only includes a range that does not include outliers. Right? So that's the range of good data, in other words. This is my interquartile range. That's my median. And here are my outliers. So the circles are mild. They're between 1.5 and 3 IQRs, either below Q1 or above Q3. And the asterisk is an extreme outlier. It's above 3 IQRs, below or above Q1 or Q3. Okay, and here's the listing of it all. Straightforward so far. I'm trying to think. Do I ask you to compute box plots in this class? I don't think I do ask you to compute box plots. I think I may ask you to interpret a box plot. Every year I change the assignment, so I'm trying to remember. I don't know, so don't quote me on that. So the important part is to be able to look at it and to just extract the information quickly. We can also depict outliers in a histogram, which is actually probably the fastest thing to do. So you can draw a histogram here and see that these guys are pretty far out there. They're probably outliers. All right. Now look at this. This is actually measurements of the speed of light in a laboratory setting. And you can measure the speed of light using, you can slow it down to crystal matrices and so forth and try to figure it out. So if you didn't know what the speed of light was and you ran 5 different experiments to figure it out, this experiment has the median speed of light is somewhere up here, this one has it down here, and you have a wide variety of guesses. By putting box plots on the same graph of my various experiments, I can see where the true speed probably lies. Now, if I were to use these experiments only, the combined score would drive it up a little bit higher here. Right, so these are not very good experiments. What we usually do with these kinds of box plots is we run meta-analyses. So a meta-analysis is when we combine the results of a variety of different kinds of studies. It's a very popular, common kind of study now. If you do graduate work, your thesis could be a meta-analysis. If you do a 4th-year independent research project, that could be a meta-analysis. With the meta-analysis in drug discovery stuff, maybe we're looking at whether or not the drug causes a significant change in something. Let's say you're testing a migraine drug, whether or not it reduces the incidence of migraine. And in this study here, we show that of all my subjects, the average response was over here. And in this study, the average response was here, and so forth. Right, so I put them all in a box plot in my meta-analysis and see what the typical response is. And I see that most of them kind of agree on these areas here. Right, so I know to ignore these extreme points here. So box plots, very, very common in meta-analyses. We usually include like a summary score as well in a meta-analysis, so we can combine all our data and figure out what the overall score is and so forth. So there's an entire career to be built around designing and doing meta-analyses. One of my grad students actually just wrote an incredible thesis on it, and he'll be rich one day. It's great. Okay, standard scores. A standard score is also called a z-score, or a z-value, or a normal score, and all it really is the number of standard deviations that your score is beyond the mean, right? So it's a measure of how far an observation is from the mean of its distribution. So I'm going to give an example. So for example, if you got 65% in this class in the final exam, how far is that from the mean? Right, how many standard deviations is that now, and why is that relevant? Well, it's relevant. Let me ask you why it's relevant. So if you score 60% in the final exam, and I ask you how far away is that from the mean score, and the mean of the class was 50%, you can say, oh, I'm 10 percentage points above the mean. Great. Why do you care if it's 1 standard deviation above the mean? Beyond 10%. Well, what added information does that give you? It's a pretty badly phrased question, I'm sorry. I'll give you the answer. So the answer is this. It's how you do relative to these people is one thing. How you do relative to another class is another thing. So maybe you want to know, are you doing better in stats, or are you doing better in biology? So maybe you got 60% in stats, and you got 50% in biology, but everybody else failed biology, and everyone else did really well in stats. So you may have got a higher mark here, but you're doing worse relative to everybody else. Does that make sense? So standard deviations let you know relatively how you're doing relative to everybody else, because you can't control for the quality of your competition. But this allows you to have some kind of quality of your competition. So the z-score, normal score, only has a meaning if you know the parameters of the reference population. The parameters of the reference population. A parameter, again, is a statistic computed for the large population. In this case, the parameter we care about is the mean of the reference population. For example, if I'm going to figure out what your standard score is on the MCAT, I need to know what the average score of the MCAT for everybody was, or for last year was, or something like that. So when you do write the MCAT, they will do that. They will compute everyone's average score and give you a z-score relative to that. And you can compare that to previous years and so forth. So yes, you need to know these parameters, standard deviation and or mu. Okay, so a standard score is an index of relative standing, right? Z-score, standard score, same thing. It's expressed in the number of standard deviations. And this is the formula for a standard score or a z-score. It is your score minus the mean score of the reference population, the parameter, divided by the standard deviation of that same population. Right? So you need to know, if you're computing your standard score for your MCAT, you need to know the mean MCAT score for everybody, and you need to know the standard deviation for everybody. And hopefully you start to see why that is. Obviously you need to know the mean for everyone to figure out how different you are from the mean, and you need to know how variable it all was. If this is like, like 1, then you know that everyone got exactly the same score and everyone got the mean, which is not very useful. But if this is large, you know that there's a variety. Yes?
Even though we're saying population and reference,
yeah,
there's still descriptive information, like we have access to these ones, but it's not actual.
I don't understand.
When you mentioned in other slides,
yeah.
These are always, you need to know, all the information from your reference. But these are scores that are available. They're not something like you're comparing it to the whole country or something like that.
It is. So in the case of MCAT, when they compute your z-score, they will compute. Let's assume you write the MCAT. I'm assuming everyone does. So let's just assume you write the MCAT. They'll tell you what your percentile rank is, right? That's the same as z-score, really. And to do that, they will have computed the mean of everybody, right? So that's the entire parameter they would compute, and they would computed the standard deviation as well for everybody. Did that answer the question? I think, maybe? Okay, good. Great. So, same thing again. So, exactly the same thing from last time. All right, so let's go through an example. So as I said, it's useful for standardized testing like the MCAS, the GRE, the SATs, and so forth. It allows us to calculate the probability of a score occurring within the normal distribution. That's the same thing as saying how well you did relative to everybody else. In other words, you scored this. What's the probability that your score was better than X% of everybody else? Right, so we use the word probability fairly specifically and loosely in statistics. Probability means what you got divided by what you could have got. So if you got this, but you could have got this score, that's your probability. So anytime you get a mark on a test, that's a probability, really. You scored 60% on your test, you scored 60, you could have gotten 100, so 60%. So hope that makes some sense. So we use that word probability kind of meaningfully. Before I get to examples, look at this. This is the number of standard deviations from the mean of a given distribution. I mentioned before that 2 standard deviations gets me about over 95%, like about 47.7 or so. I forgot the exact numbers either direction. Exactly 1.96 standard deviations in either directions gives me exactly 95%. And, right? So we like 1.96. It comes up a lot in statistics because 1.96 standard deviations or a z-score of 1.96 or a standard score of 1.96, they all mean the same thing. 1.96 standard deviations in either direction from the mean gives me exactly 95% of all the respondents. And this comes up in so many tests we're going to do this semester as we trying to get, are you better than 95%? Is your test result, is it more probable than if you've repeated the test 95% of the time, and so forth. Okay. So for a variable distributed normally, 95% of the observations tend to fall between 1.96 and minus 1.96. So here's an example. The LSAT is the law school admission test. It's like the MCAT. So we know the LSAT score in Canada is normally distributed. This is a known fact. The mean mark is 60% this year, and the standard deviation is 15. Okay, so we have this data, everyone wrote the test, and the people back at the LSAT headquarters say, oh, the mean of this and that. So we want to know what is the lowest mark amongst those who are the top 10% of performers. Why do I care? I care because I'm only going to accept the top 10% this year. Right, now the top 10% this year won't have the same mark as the top 10% last year, because this year, maybe they're really good. Or maybe they're really bad. I don't know. I can't use the same mark cutoff year to year because I can't control for the quality of students year to year. So I'm going to say I only want to take the top 10%. So to make my life easy, I want to compute what the lowest mark is for that top 10%. Let's see how that's done. All right, look at this scary, scary notation. So there's a probability of having a z-score greater than 10%. Right? So that 0.1, that's 10%. That's all that means. This is my z-score formula. I have x minus my mean divided by my 15. Because my mean is 60%, my standard deviation is 15. Okay, I put the notation in here just also, 1, to scare you, and 2, to show you this is how it's done. Now, what do I do with this information? I look up in a table what 10% means. There are z-score tables, z-score calculators. This is the element that sounds like cheating, but it's not cheating. Someone else has done the hard work. Computers have done the hard work, created large amounts of normal distributions to figure out that a z-score of 1.282 corresponds to 10%. Let me go back for a second, sure where that comes from. Back here. There we go. Okay, well, one more. 2 more. Oh, back here again. That's good. All right. So 10% is going to be 2.3 over here somewhere. So we know that 1.96 is over here. And 10%, yeah, right here somewhere. Right? So we're looking for a standard deviation of 1 point something. Here's 1 and 2 standard deviations. It's going to be between 1 and 2. It's going to be over here somewhere. That'll give us the top 10%. We want to know exactly what number is going to be between 1 and 2. It's probably about 1 point 2 something. Now I know There we go. Now we know by looking it up, it's 1.282 exactly. In the good old days, before computers, we'd actually have tables we look up. And when you do your exams, you're going to have tables that you look up. And also in the good old days, if we didn't have tables, we'd estimate, oh, it looks like 1.3, it looks like 1.1 something. But we know it's 1.282. So I plug that in there, and that is the same as my formula. So now the z-score of 1.282 is the same as my z formula, which is my score minus the mean or standard deviation. I solve for my score, and I get 79.23. So 79.23 is the base score above which you got 10%, 90% or higher. Okay. Phrase that clumsily. Okay. And by the way, you can look up, here's a link to a z-score calculator online. There are literally thousands of them if you Google z-score calculator. Okay, in the back of your book as well, textbook, there's a z-score table. Now let's use a z-score to compare tests. So let's say, like the example I gave you last time, you have a student in 2 classes, English and math. And she got 70% in English and 72% in math and wants to know in which class she's doing better. I've already explained this, but I ask you again, why isn't it obviously math? She got a 72 in math and a 70 in English. Why isn't she automatically doing better in math? Yes?
Because everyone else could have failed English, but they could be doing really, really well at math.
Exactly. Maybe she got a really easy teacher in math, right? She got Deonander in math, and the scores were all too high. Right? So we don't know. So we're going to figure that out. So here are the data for the 2 classes. In English and math, the mean is that, and standard deviation is that. And here are her marks. Her marks are the x's. The distribution means are these, and the distribution standard deviation are these. Right? And you can do this too. Can you do this? Maybe you can do this. Maybe I will give you the mean and standard deviation for your exams. You can figure it out yourself. And you can ask other professors their means and standard deviations, and you can figure it out yourself which class you're doing better in at the end of the year. Okay, so let's figure it out now. These 2 marks are from different distributions. So what we're going to do is compute a z-score for each one, and to see which z-score is higher. Right? So the z-score is the relative standing, the standard score. It's the number of standard deviations above the mean. That's all it does. So let's compute that. So for English, we plug in the numbers. We get 0.67 for math. We get 0.7. Oh my goodness, it's the same. So what can we conclude? Same z-score for both classes. What do we conclude? Which one is she doing better in? Yes, sir.
She's doing equally well.
That is correct. She's doing equally well. Right. Yeah, we have a null response. Equally well. Okay. So she's doing, let's interpret, she's doing 0.67 standard deviations above the mean in both classes. If it was a minus, by the way, she'd be doing 0.67 below the mean in both classes. But she's actually doing better than most people in both classes, but she's doing equally amounts better in both classes. So she's a consistent performer. Right. And again, I can go back to my z-score calculator, plug in that number, and I get 25.1%, meaning she's in the top 25.1% of the class in both of these. All right. So some things to think about. Standard scores have a mean. If I take all the standard scores in my sample and add them up and all that, I have a mean of 0, standard deviation of 1. I can transform them, as asked earlier. So I use transformations to change the shape of my distribution. So what we do for the GRE and the SAT scores is that we transform it so mean is 500. For IQ tests, the mean is always 100, believe it or not. So every time a bunch of people write IQ tests, they're transformed so that we can tell how much better you're doing than 100. And average IQ score is always 100, and so forth. Okay. Moving on to the central limit theorem. The central limit theorem is this theorem that any large numbers of samples of any given random variable will eventually form a bell curve. Now, sometimes this works. Let me see. It doesn't work all the time. I'll click on this and see if it works. So, fun little applet. Let me see. Let me see this work. Dun, 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 dun. No, of course not, because the Java's not running. That's just great. Okay. Screw that then. So if he tries it on, if it works, what it does is shows you a little animation comes up, and you keep clicking on it to add more data, random data to the sample, and the more you add, the more normally distributed it becomes. That demonstrates the central limit theorem. So why is the central limit theorem important? It's important because it allows us to assume that if you have sufficient data, that your data probably conforms to the normal distribution, which means it probably means we can use standard scores. It probably means we can use all kinds of other fun stats we're going to learn about this semester. But it begins with assuming a certain kind of distribution, and we like to assume the normal distribution. There are other kinds of distributions. There's like a Poisson distribution, binomial distribution, and so forth. If you go further in statistics, you learn about those things and want to kill yourselves. But knowing about normal distribution is good enough. It covers the majority of what you want to know about. So again, some things about the normal distribution. 68% of values drawn are within one standard deviation. So I've covered that already. 34.1% one way, 34.1% the other way. Together they're 68%. 95% is 2 standard deviations away. 99.7% are 3 standard deviations away. Some people call this the 3 sigma rule. So a sigma is 1 standard deviation, right? So 3 sigmas away from the mean, you get 99.7% of all your samples. If your data point is more than 3 sigmas away from the mean, you got an extreme case. So that the 5-year-old Peruvian girl who gave birth, she's clearly beyond 3 sigmas from the mean average or age of someone giving birth. Right? So here it is, a 3 sigma rule, and this is, don't worry about the notation too much. Hope that doesn't scare you too much. All it says is one standard deviation, 68% of cases, 2 standard deviations, 95% of cases, 3 standard deviations, 99.7% of cases, right, and so forth. It's a lot of stuff. Any questions? No, yeah? Crystal clear? Yay. That's your homework. See you later.